Okay, so here's a question for you. What is a number? I mean, really? It sounds like the simplest question in the world, right? Something you learn before you can even tie your shoes. But as it turns out, the real answer? Well, it's going to take us to the very edge of the universe and deep into the foundations of logic itself.
All right, let's just dive right in. Seriously, take a second. Try to answer that for yourself. What is a number? You use them every single day, you know what they do, but what is one? And I'm guessing you probably came up with something like this, right? It's a symbol for counting things or for measuring how much of something there is. It's the common sense textbook definition. And look, for most of life, that's totally fine. It's all you need. But for mathematicians, oh, that's just the starting line. See, if you're going to build this entire incredible structure that we call mathematics, your foundation can't just be, well, it's for counting apples. That's way too shaky. No, you need something solid, something rigorous. You need a formal set of rules for the game. So to make things really rigorous, mathematicians basically came up with two main ways to do this. Now, you don't need to be an expert on this stuff. The core idea is pretty simple. One way is to just define numbers by their properties. You say, okay, there's the starting point, let's call it 0, and every number has a next one, a successor. The other way is to literally build them from the ground up, starting with the simplest thing imaginable, nothing. An empty set. But here's the key thing to get from both of these. A number, formally, isn't a physical thing you can hold. It's a pure concept that just follows a perfect set of rules. But this is where things get interesting. This is where our perfect, solid foundation starts to get its first tiny crack. What happens when we use these perfect rules to create numbers that are so ridiculously huge they just defy reality itself? Okay, just look at this number. That's a 1 followed by a googol zeros. And a googol, that's 10 to the power of 100. Now, to put that in perspective, there are only about 10 to the 80 atoms in the entire known universe. You could literally assign a digit to every single atom, and you wouldn't even make a dent in writing this number down. It is physically impossible to express. Period. So if we can't ever write it down, how in the world can we work with it? Well, we have to shift gears, right? Mathematics stops being about juggling individual digits and starts being about manipulating symbols and definitions. We don't need to see all the zeros to know its properties. We can still compare it. We can still do arithmetic with it, all just by working with its nice, compact, symbolic name. See, math isn't stuck in the physical world. And this brings us right to the heart of the whole paradox. Is that elegant little symbol you see on the screen, is it really the same thing as the impossibly massive number it's supposed to represent? I mean, this is the critical question. Our formal rules say a number is just this long chain of next ones starting from 0. But if we can never, and I mean never, under any circumstances, actually write out that entire chain, is this expression really a number in the same way that, say, the number 3 is a number? And here is the beautiful, elegant solution. The answer is no. The symbols on the screen are not the number. They're a name, a label. It's just a well-formed expression that acts like a super precise pointer to one single, unique spot on that abstract, infinite line of numbers. We never actually touch the colossal number itself. We only ever work with its name. Okay, but hold on a minute. Our rules say these names have to be finite strings of symbols, but what does finite even mean if the string of digits would be longer than the entire universe? It kind of feels like we're cheating here, doesn't it? All right, to solve this, we got to look at the formal definition. And here's the trick. In math, a string doesn't have to be physically written out. Not at all. It just has to be defined by a finite rule. As long as we have a rule that can tell us exactly which symbol goes in any position you ask for, the first position, the billionth position, the googolth position, then that string formally exists. The rule itself is finite, even if the thing it describes is way too big to ever write down. And this is the crucial insight. For something to exist in the world of mathematics, it doesn't need to be physically written down or built or even completely imagined in your head. Its existence is purely logical. All it needs is to be uniquely definable by a finite set of rules and symbols. That's it. And that one idea, that existence is all about definability, well, that leads us to a truly stunning, mind-blowing revelation about what numbers really are. So here's the ultimate test, the final checklist for whether a number formally exists. First, you need a formal language, a fixed set of symbols and rules. Second, you have to be able to create a finite expression, a name, using that language. And third, and this is crucial, that name has to point to one and only one unique number. If it passes that test, it's a real number. If it fails, it's a ghost. This simple rule just split the entire universe of numbers into two totally different categories. On one side, you've got the definable numbers, the ones we can actually give a finite name to. But on the other side, you have the undefinable numbers. These have no finite description whatsoever. And here's the truly shocking part. The numbers we can actually define, they're an infinitesimally tiny minority. I absolutely love this analogy. Think about every number you've ever even heard of. Pi, E, a Googleplex, Graham's number, any of them. They aren't typical at all. They're special. They are these tiny, cherry-picked islands of definability that we were just lucky enough to be able to describe. And they're floating in this vast, unending ocean of numbers that are fundamentally, completely unnameable.
So why are there so few? It really just comes down to a simple counting argument. Think about it. How many different names or descriptions can we possibly write down? Even if we use every symbol we have in every possible combination, we can only ever create a listable number of names. It's a type of infinity, but it's a countable one. But the total number of theoretical numbers out there, that's a higher order of infinity. They can't be put into a list. This means we have infinitely fewer names than we have numbers that need naming. So what does that mean? It means if you could somehow pick a number completely at random from the infinite number line, the probability that you'd land on one of the special ones we can actually define is zero, essentially zero. That's what you're seeing here, the chance of finding one of those islands in that vast ocean.
And that is the final mind-bending takeaway. So what is a number? It's not just some point on a line. A number, in the only way mathematics can actually handle it, is an idea that can be named by a finite set of rules. And this means that the vast, overwhelming majority of numbers you might imagine out there on that infinite line, they don't formally exist. They're ghosts, phantoms in the mathematical machine, forever beyond our reach. So the next time you write down a number, any number at all, just remember it's one of the special ones. It's a tiny, definable island in an endless, endless sea of the unnameable. So, how does that change the way you see math?